Exactly. Just because I'm back to me, I'm not going to get an A in the class.
And I try to draw it. And
I'm still going to get an A.
I know the equation.
Yeah. I'm neither one. The only class I actually talked was this class. I don't know if that's a good thing or a bad thing, but.
And you said I was dumb for making a matrix. Come on now.
It still works.
Yeah.
Oh, yeah.
Only.
Yeah. 7 p.m. on Thursday.
Like, I would not be able to eat afterwards. Like, I think I would take up all of Markham after that class. Like, after one lab, I'm already done. After 2 labs, I'd be like Yogi Bear.
I think he just got a new nickname. I'm waiting here to. I think we're missing Mr. Hodgkiss. So I didn't want to wait. Didn't want to start. We've got a lot to do today. Yeah, he's in ROTC, isn't he? Yeah. So let's begin. A good quote from St. Thomas Aquinas: "Quid recipitur ad modum recipientis recipitur." Miss Shaven is the only one who admits to knowing any Latin. So, yeah, and a little German too. So, quid, whatever. That's a great word. You know, when my kids try to say that to me, I said, at least do it in Latin. Quid recipitur ad modum. Whatever is received in the mode of the receiver. This is typical Aquinas. He's trying to make the most general statement that he can that will apply to what he's talking about. So he's receiver. What is a receiver? Well, it could be a physical object, a body. You know, baseball hits the bat. The bat hits the baseball. You know, the ball is the receiver of the action of the bat. Could be that. Could even be something like a learner, a student, who's receiving knowledge. In any case, whatever is received in the mode of the receiver, not the teacher. So whatever is received by the student depends on the student's preparation and openness to receiving. Right? So what determines your mode as a student? Well, preparation certainly comes into this, no doubt. If you are familiar with certain steps in algebra, things that when you're learning vector algebra, it builds on what you know from the ordinary algebra. If you don't know some basic trig, you're not going to receive dot product and cross product in terms of cosines and sines. That won't make much sense to you. So you have to have some preparation to receive these things. You have to be open, willing. This is hard work. This subject is not an easy subject. And it requires a lot of work. And what you will receive is not going to be something you're going to receive just passively sitting in class listening to me. Most of the learning happens outside of class. And that's just the way this subject is. You're going to have to grapple with it and really wrestle with it. And in fact, you can take some heart from it. If you're confused, that means you're about to learn something. And if you're really confused, you're about to learn something big, right? So you can kind of take heart from that, but you're going to have to persist. The only way to resolve the confusion for you is to work hard at it. And I'll help in class, help you to hopefully learn how to resolve confusions as we go along and teach you some ways to think about it, but it's entirely mental, right? You've got to be able to isolate this. So if you're working on your homework, you can't figure it out, if you've done some work on it, I'm happy to have an email. Just writing an email will help you to focus what your question is about. So a question like, I don't understand chapter 2. It's hard for me to work with that one. But if you say, he says here in the text, yada, 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 but I know that this is true, and there seems to be a conflict between the two, and I know that there must be some way to resolve this, so how do I think about this, right? That's a good question in an email. And I'm often receiving emails through the day, so checking my email, so that's a good way to do it. I have office hours on Friday only, though, because that was the most popular times on the poll that I sent out. 3 different hours on Friday, 2 hours before class, 10 and 12, and then I have a break for lunch in there, and then 2:30 to 3:20 after class. So, but only on Friday. I love teaching this class, but it's not the only thing I have responsibility for. I have other things I have to do, so I can't. And usually the way I find that was questions, for me, what works best is if you have some question, fundamental question about the general understanding. And those are, but I'm happy to help more detailed questions, that's fine. But you're not going to be able to sit in my office and work through your homework, right? That's not going to happen. You come with me with a specific question, we answer it, and you go somewhere else to work. You can't sit in my office and do your homework. You can, however, sit in the Physics Learning Center and do your homework. And there are, just a few minutes ago, there were 2 graduate students in there. So there's always one during times when they're open, which I think is almost all the time during the day. And I think they've even got some evening hours. I'm not sure of the exact times. I sent them out earlier in the term. It's in 223 Kynard, which, do you remember the first day of class over in Kynard, half of you were standing outside in the hallway? That's the Physics Learning Center, where you thought you were waiting for the classroom. That's the Physics Learning Center. So it has the same number as the classroom. There's 2 rooms with the same number. That's confusion. So anyway, it's the other one. It's the smaller one. And that's a good place for you to go for figuring out how to do cross products, dot products, detailed things like that. Okay? And as I said, they're open a lot. So, and they're very experienced students. They should be good help. There are other sources for tutoring, too, in the Academic Success Center. But I would recommend you try the graduate students in the Physics Learning Center first. And if their explanation is, maybe up here, pull them down. Tell them, I don't understand that. I need to bring you down, right? Argue with them about it. Make them work for their money. They're getting paid.
What?
Yeah, they're getting paid. So make them work for their money. If they can't explain it, make them work, right? Another way you could say, if you can't explain it in simple terms, this is the first day of class, remember this expression, if you can't explain it in simple terms, you don't really understand it. That applies to you as well, but you can use it on the graduate students. So challenge them to explain it in simple terms, right? Because it's learning for them. Okay, so we are going to go through the homework today, but I want to pick up at the end of the lecture that we did last time. We had done, you remember, multiplication, vector multiplication. This is at the end of the last lecture. Vector multiplication. And we did it 2 different ways. So there's both dot product and cross product. And we did it 2 different ways. One way, which is the primary way, the way I prefer you to learn, is in terms of magnitude and direction. Because that's what vectors are primarily. The second way, which is an easy way, usually the way we will calculate most things, not always, but is in terms of the Cartesian form. Now we had done dot and cross product in terms of magnitude and direction. And we had done the Cartesian form for the dot product, so the very last step that we didn't finish in class was to do the cross product in Cartesian form, right? There was dot and cross. There was, in terms of magnitude and direction, and then in terms of Cartesian form. So we did the dot product, and we're filling out this last step here. And I also did this only in 2D. I'm going to finish that. The three-dimensional should be able to figure it out from knowing the two-dimensional. So, but it's a good place to start, two-dimensional. And in the book, it's fully three-dimensional. Okay, so we have generally two vectors written in Cartesian form. So when I say I'm doing it from Cartesian form, so this is today here. This is today. So in 2 dimension, I have my Cartesian vectors, and these are two completely general vectors. These could be any two vectors in the xy plane. But notice that, how about the z component of A? What is it? 0. Right. So I could write 0 times z hat. That's kind of silly, so I don't do it. And 0 times z hat. So these both have no z component. They're completely in the plane. So this plane is defined by two unit vectors, x and y, x hat and y hat. And these are two completely general vectors in the plane. Now, I showed you how to do the dot product before. And this is very similar to one of the homework problems, so you'll see this again in just a minute. Except that it's, except that it's two-dimensional. And your homework was three-dimensional. Okay, so let's take the dot product between these two vectors. Just to show you, remind you, this was on the previous lecture. Okay, now I have two terms here, and I have two terms here. And I'm multiplying them together. I'm going to distribute multiplication over addition. Now notice this is vector multiplication, specifically dot product. And it's vector addition. So it's not exactly the same as what you were doing before, but we're going to try to develop an algebra where those same rules apply. So in other words, we're going to use the distribution law. So I have two terms multiplying two terms. How many terms will I have if I do that when I'm done? 4 terms. Thank you. Oops, excuse me. See, I'm already making a mistake here. Okay, so I'm going to write down the 4 combinations. And so I have a term on the left-hand side and a term on the right-hand side. The first one is this one, then this one, then this one, and that one. So I have 4 terms. I'm going to write them all out here for you.
Would it be AX, BX?
Excuse me. Yeah, thank you. Thank you, thank you. Mr. Vestal and somebody else. They're quietly. And I'm about to do it again. Here we go. All right. Got to get myself into gear here. Okay, start off with 4 terms. No, that's right. Right? Is it correct? Looks okay to me. I'm entirely capable of making mistakes up here, so, and that's the problem with me sending you PDFs of this stuff, is it may have an error in it. So I'm really glad if you speak up and ask questions. Okay? You see where the 4 terms come from? See, puzzled, looks a little bit puzzled. This and this, this and this, this and this, and then this and this, and there's an addition between all of them. Okay, so 2 of these terms vanish, though, because x hat and y hat are perpendicular to each other, and the dot product vanishes. So these 2 terms right here in the middle are both 0. And how about x hat dot x hat? It's 1. Remember the definition, the fundamental definition of a vector dotted into another vector is the length of one vector times the length of another vector times the cosine of the angle between the 2 vectors. Well, if it's x hat with x hat, the magnitude is 1 times the magnitude of 1. The cosine of the angle is 0. The angle is 0, so the cosine of 0 is 1. So x hat dot x hat is just 1. And the same thing for y hat dot y hat. So this is, in 2 dimensions, is just ax bx plus ay by. And you can guess in 3 dimensions, when you extend this, which is one of the first problem from the book for today, you get an az bz. If I have 3 terms here, suppose I write a 3-dimensional vector in each case, I get 3 times 3. How many terms do I start off with? 9. Again, 6 of them vanish because the vectors are perpendicular. You're just left with 3. Okay, so we'll see that in a minute. Now, my point is, we did this at the end of class last time. Let me now turn to the cross product with the same 2 vectors. I want to study A cross B with the same 2 vectors. And so I want you to be able to do this. And here is where we will start to understand why it is that this notation, which appears to be a little redundant, is a helpful notation here. Okay, I have 2 terms on each side, but I have a cross product. So how many terms am I going to have? Again, 4. So let's write them out explicitly. Ax, bx. And it's very much the same as what we had before, but instead of a dot product, we have a cross product. Now, it's very important to get the order correct here of these cross products. The dot product is commutative. Remember, A dot B is the same thing as B dot A, but the cross product is not. So it's very important to keep the cross product order correct here. So notice here I have x hat cross y hat on this term and y hat cross x hat on this term. Those are not the same. And it's important to keep the order the same. Okay, 2 of these terms are not like the other. Two of these terms vanish. Any Sesame Street kids here? 2 of these terms are not like the others? No? Goodness gracious. All right. So, 2 terms vanish. Which 2 vanish? Yes, sir. Exactly right. So the cross product of a vector with itself gives 0, right? Because it involves there are lots of ways to think about it. It's the area of a parallelogram formed by it, but that's collapsed to nothing, so there's no area involved. It's the amount of the 2 vectors perpendicular to each other, but if it's the same vector, it has no part perpendicular to itself. It involves the sine of the angle, and the angle is 0, so the sine of 0 is 0. So there's 3 different ways to argue the same thing. Cross product of a vector with itself gives 0. So these 2 vanish. And how about x hat cross y hat? Let me erase that. Yes, sir. Right. This, let me put it in red here. This thing is z hat. X hat cross y hat is z hat. So let me draw go back to the previous page. Go down to the bottom here. There's that figure, x hat and y hat. I'm going to draw on this figure here a 3rd vector, z hat. And it's like the head of the arrow is coming out at you from the board. That circle with the dot means it's coming at you, whereas so this means it's out of the board. And this means you see the tail feathers, right, into the board. Okay? That's a way of drawing a vector in and out of the plane. It's a little hard to draw. But so go back to that. X hat cross y hat. God bless you. Put your fingers in the direction of x hat. Put your fingers like that. Put your palm in the direction of the 2nd vector. So x hat cross y hat comes out of the board. How about y hat cross x hat? Y hat cross x hat is into the board. So y hat cross x hat is negative z hat. Thank you. So this is negative z hat. It's just in the opposite direction. So collecting the terms here, it's ax by minus ay bx, and that's why it's important to get the order correct because of that negative sign. Okay, there's the vector cross product. Notice the 2 vectors are in the xy plane. The cross product is going to be out of that plane. They're not going to have any component in the xy plane. It's all along z. And this is in fact the area of the parallelogram. May not look like, may not be obvious, but it's actually the same as what we were doing before. It gives exactly the same result. And that's what some of your homework is to demonstrate to you, that all of these different ways of doing the calculations give the same results if you do them right. Okay, so any questions about those so far? Yes, sir.
To make sure I'm understanding right, so understand x hat times y hat is z, and y hat times x hat is negative z hat.
Yes, sir. Z hat.
So how does it make it a sub x, b sub y minus a sub y minus b?
There's a negative sign right there.
Just makes the entire thing negative. You put it there,
right.
And then
You factor out this.
okay, actually that makes sense.
Z hat is common to both of these. They're both either along Z or in the opposite direction. And remember, these components can themselves be positive or negative numbers, right? They're symbols that stand for numbers. Is it true that I did the magnitude and direction explanation of the cross product in class? I did that, didn't I? Did I not do that one? All right. Then we better take the time to do that one. Okay. I'm sorry. I'll go back one step. So here's the cross product. I should have done this first. I'm sorry if I got ahead of myself a little bit. The cross product in terms of magnitude and direction. Just like the dot product, remember the dot product in terms of magnitude and direction is AB cos theta, where that theta is the angle formed by the two vectors. Okay, notice the dot product is itself a scalar, just a number. It can be positive or negative, but it's just a number. The cross product is a vector. So this is also called either cross product, also called vector product. Whereas this is called a dot product, also called a scalar product, for the reason that one is a number and one is a vector. Okay, so let's study that's in terms of magnitude and direction, right? The magnitude of A, the magnitude of B, and the angle between the two tell us about their relative direction. How are they oriented relative to each other? Okay. Now, the other thing you can do with this, here, let's draw A and B. Here's A and here's B, let's suppose. Now, let's take the, I'm going to draw a line here, which is, let's do it in red. It makes it a little easier to see it. A line here perpendicular to A. I'm going to draw a line that goes straight down to A, forms a right angle. And so I now have formed a right triangle, and I'm going to pull it off here to the side a little bit so you can see it. So this angle theta here. And what is the hypotenuse? That's not very clear. Let me make it a little bit bigger. What is the hypotenuse of that triangle? What is the length of the hypotenuse in that triangle? It's the magnitude of the vector B. Okay. So, if I have the hypotenuse and the angle, what are the two sides? It's trigonometry.
B sine theta and B cosine theta.
Right. Which goes where, Mr. Vesta?
The one on the right is sine, one on the bottom is cosine.
Good. B sine theta, B cos theta. Now, these are also called, given names, B parallel, meaning the part of B that's parallel to the direction of A, right? Because that's how we're doing this. We're breaking B up into two pieces, a part that's parallel and a part that's perpendicular. And the other part is B perpendicular. So I could write the dot product as A dot B, which is going to be A, the magnitude of A, times B cosine theta, which is B parallel. B parallel is B cos theta. And A cross B, I could write, again, that unit vector perpendicular to the plane, and then I could write it as AB perpendicular, because B sine theta is the perpendicular component. And AB perpendicular is the area of the rectangle. It's the area, also the area of the parallelogram. Right? So you can see why the cross product, the magnitude of the cross product, is the area of the parallelogram. Okay, that's in terms of magnitude and direction. And then this is in terms of the Cartesian components for the cross product. Can you see the relationship between dot and cross product? Yes, sir. Mr. Vesta.
So
is there a graphic representation of what exactly is the cross product on there? Like, is there a specific line that is the cross product?
No. The cross product being a multiplication is not a specific line. So it's the magnitude of A times this piece. So if you could represent, I don't know how to represent the product of two numbers as a line. Right? Now I can do it for the cross product because that's an area. And so it's the area of the parallelogram. But if I'm talking about the dot product, I have the magnitude of this times this piece, which is the amount of B that's projected onto the direction of A. And I don't know how to draw a line which has length, which is the product of two lengths. See, I don't know how to do that.
Okay.
But there was something in the book. What does he talk about in the book, Mr. Avery? Do you remember this question you had? You wanted an explanation for dot product. Did you look in the book?
Yeah, I looked in the book.
Good.
What are you specifically talking about?
So he has the section where he's saying first principles explanation of dot product. What does that mean? First principles explanation of dot product. What does that mean?
Like how to understand it in terms of our senses.
Basic.
Senses.
Yes, right. What is it? Give me a physical understanding. We're saying math is physics, really. Math is study of quantity. Quantity is a basic attribute of physical things. So math is a part of physics if you understand it that way. So we should be able to understand it physically. So what is his understanding of the dot product? He gives a physical explanation for it. Yes, ma'am.
He means traveling northwest a certain distance. How far of that distance was he going west?
Good. Okay. Suppose the vector A represents traveling a distance A along the direction A hat, right? The combination of magnitude and direction. So the distance is A, which is the magnitude or length of the vector A, and the direction is given in terms of the unit vector that points the direction. Magnitude and direction. Okay, how far east did he go? Can you express that in terms of a dot product? How about if we have E hat is the unit vector in the east direction? And we take the dot product of that with this vector. That's it. That's how far east. It's also the distance times the cosine of the angle formed by this angle formed by east and A, right? So this is the east direction, and this is A. That angle is theta. If theta is 0, then you're going perfectly east, right? And you'll get everything, all your motion is in the eastern direction. If the angle is pi over 2, you're traveling north, and you're not making any progress east. The dot product is going to be 0, because the cosine of pi over 2 is 0. And if the angle, what if you're traveling west, then it means you're traveling opposite to east. And every step you take is getting you farther away, which means this dot product will be negative. Right. So if the angle is pi, cosine of pi is -1, and so what you're getting, the dot product is -A. Every step you take gets you farther, exactly that distance farther away from your destination. That was in the book. Okay? That's physical understanding of dot product. Okay, so now let's go over the homework. Beginning with the worksheet. So you had lots of questions just to work out mostly in terms of Cartesian components. Most of this is just exercises in terms of the Cartesian forms. So we have two vectors A and B. We just add the components. There's a typo here, number 2 on the solution. That should be A minus B. I repeated A plus B, and then it said A plus B. It should be A minus B. The answer is correct. The solution is correct, but I wrote A plus B there. So let's do 2. A minus B, where A is equal to 3x plus 3y. And we subtract from that a vector B, and notice that B is now 2x minus 1y. And the negative sign out in the subtraction applies to all the components inside the parentheses. And so this is just like a regular algebra in that sense, except we're keeping the x hats and the y hats separate. So this is x hat plus 4y hat. Right? Is everybody clear on that? That's in terms of Cartesian components. So you can see the calculation of vector sums and multiplication, things like that, made much easier more ordinarily in terms of Cartesian components. Not always, but straightforward anyway. You can crank it. Okay, dot products. So number 3. Okay, now what I'm looking for here, for the time being, I want you writing out all of these products. And I know it seems kind of tedious, but I want you to write them all out. How many will there be? How many will there be here for this 4 again? So it's going to be 9 times x hat dot x hat plus 9 times y hat dot x hat plus 9 times x hat dot y hat. I know it seems a little bit belabored, but I want you really to understand all of these steps. So, and then 2 of these vanish, boom, boom, and 2 of these are reduced to 1 here. So the sum is equal to 18. Notice this is a number. It's not a vector, right? Dot products produce a number. How far in the east direction did I get? Something like that, right? It's going to give you a number. So what is this in relation to the length of A?
Square of the length.
Correct. Yes, sir. This is the square of the length of A. So this could be written either as A squared or it could be written as the vector with the vertical bars, meaning the magnitude of A squared. Either way. So the length of A is square root of 18 or 3 root 2. I don't like decimals ordinarily. Root 2 is precise. Writing 1.41 is imprecise. Square root of 2, nice and clean thing. Don't worry about calculators and decimals and stuff. For the most part, sometimes I'll have you do something, but for the most part, that's fine. Okay, r dot r. Again, this is a position vector. So r is given in terms of 3 distances. I could write this vector. I could write this as r sub x, x hat, plus r sub y, y hat, plus r sub z, z hat. Sure, no problem. That's fine. Means the same thing. Either way. Everybody see why r sub x, what that means is the part of r in the direction of x, which is what we sometimes call x. So shorter, in some cases, just to write x, y, and z. Okay, and now, as you can see, I'm going to take the dot product with itself. And there are 3 terms. This is a 3-dimensional vector. How many terms am I going to get? 3 and 3. I'm going to get 9. Right? And you can look at the solution here at the bottom of the page, page 1. You can see I've written out all 9 terms. And actually I've combined pairs of them. But because the unit vectors are perpendicular to each other, all but 3 terms survive. And so this is just going to be x squared plus y squared plus z squared when all is said and done. But I want to see the work in between, and that's what's on here. Okay? Do you need me to go through this again? It's very much like what I did before with the A and the B, just a page ago. Oops. So let's go up to not a page ago, a little bit farther, right here. Okay. Here's what I want you to do with R, but you notice I have 3 components because it's a general vector in 3 dimensions. These are restricted to 2 dimensions. And when I multiply them out, I get 3 terms. I get 9 terms, 3 by 3. Okay? That's what I'm looking for there. Now, your understanding might be enough to allow you to skip this, but like I said, I really skipped the intermediate steps, but I'd really like you to practice those intermediate steps and be able to do them. That's really important. I may ask you specifically on a test, I want to see all of those steps. Expand out this product, show me how it works. Okay, so, all right, here's another one. We have 2 vectors, A and C. All right, so first, find the dot product of A with C. So A is 3x hat plus 3y hat dotted into minus 1 x hat. Okay? Now, you should be able to see you're going to, when I distribute the product, I'm going to get two products. I'm going to get minus 3 times x hat dot x hat and minus 3 y hat dot x hat. One of those terms vanishes. Which one?
X hat times y hat.
Right, that one. And what's x hat dot x hat? 1. So this is negative 3. What does that say about A and C? What about their directions? What does it say about them? The dot product is negative.
They're in opposite directions.
Yeah, they've got some components. In some sense, they're in opposite directions. So they're going more in opposing directions than they are in the same direction. If the dot product is negative, that's what's going to happen. Okay, now how would you calculate the angle between A and C? You know the dot product. How do you calculate the angle? Thoughts about that? Yes, sir, Mr. Trimley.
I'll answer that too, but I also kind of have a question.
Okay. All right, go ahead. You're answering a question with a question.
Sort of. Since the equation for dot product is vector A times vector B equals AB cosine of the angle formed by AB.
Yeah. Right?
Why is the answer to that just negative 3? Why don't we multiply that by the cosine of the angle?
Okay, you just answered the question. All right, it's
So
the length of A. You did answer your question with a question. The length of A times the length of C times the cosine of the angle between the two vectors. So we need to find the length of A and the length of C, and then we can find the cosine. So the cosine of the angle between the two is A dot C over the magnitude of A and the magnitude of C. That gives us the cosine of the angle. So we need to find the length of A and the length of C. And we found the length of A earlier. Right? Remember, A was 3 square root of 2. So what is the length of C? And you can look up at C. C is just negative 1 x hat. It's the magnitude of negative 1 x hat. So how long is that? It's not negative. Magnitudes are always positive. It's 1. Okay, so what's A dot C is negative 3. And what is the magnitude of A is 3 root 2. And the magnitude of C is 1. So this is minus 1 over root 2. The cosine of the angle is minus 1 over root 2. What's the angle?
It's 3 pi over 4.
Yes, sir, 3 pi over 4. Are they heading in opposite directions, more or less, or in, yeah, they're, because the angle is 135, 3 pi over 4. They're mostly in opposite directions.
So this leads me back to my question.
Oh, okay, sorry.
Because I knew what the angle was because I drew a picture.
Okay, good.
And
good.
I mean, I could kind of just see it.
Right.
But
this is a way of doing it without drawing a picture.
right. And it comes out to the same answer. Cosine of theta is negative square root of 2 over 2.
Right.
So why don't you multiply those two together?
You did. Well, multiply what together?
Like.
Okay, so let's check it out here. A, so let's do A dot B. Let's use the magnitude and direction formula, which is AB C. Excuse me, this should be C here. AC should be AC cosine theta. What's the magnitude of A? 3 root 2. What's the magnitude of C? 1. What's the magnitude of the cosine? Minus 1 over root 2 is negative 3.
Okay, so I think I was misunderstanding. Was that AC I thought was negative 3.
Right. A is 3 root 2. So let's draw these two vectors like Mr. Trimley did. Let's go ahead and draw a picture of them and see what they look like. A is, so let's put it on a Cartesian coordinate system. 1, 2, 3, 1, 2, 3, roughly speaking. A is here. And where is C? C is negative 1. So this is negative 1 x hat. This is C. And this is A, which is 3 x hat plus 3 y hat. Okay, so can you see that the angle is 3 pi over 4, right, between them? And you see that, what is the magnitude of A? It's 3 times the root 2. That's the magnitude of A. That's how long A vector is. And the C vector is magnitude 1. So now you can see that the dot product will be AC cosine of the angle. The magnitude of A is 3 root 2, the magnitude of A. Magnitude of C is 1. And the magnitude of the cosine is negative 1 over root 2. So the dot product is negative 3. See how it works? So there's more than one way of doing it. They should all give the same answer. And I want you to be comfortable with the magnitude and direction way of doing it, because sometimes that's simpler, but certainly you can kind of get a feel for whether this thing should be positive or negative, or how big or how small. Okay? Good questions. Okay, so it does the same thing between C and D. C dot D minus 1 x hat, and D is 2 y hat. So this is minus 2 times x hat dot y hat. What is that? This is number 6. 0. What does that mean about C and D? Right. They're heading in, they're normal to each other. So what's the angle between them?
90
pi over 2. So this should also be CD times the cosine of the angle. What's the magnitude of C? 1. What's the magnitude of D? 2.
Oh, yeah,
And so the angle must be pi over 2, right? In order, cosine of pi over 2 is 0. Because the cosine is 0. Cosine of theta is 0 implies that theta is pi over 2. Got it? Okay? Okay, moving along to cross products now. All right, so number 7. Okay, so we have a vector, and we're, I'm going to just go ahead and do the cross product of A with itself. Now you should already see that this is going to give a simple answer. What is the cross product of any vector with itself? It's always 0. So you can see this ought to get 0 before you start doing it. You know that much. So if you don't get 0, you've done something wrong somewhere. So this is a good exercise. Okay. Now one way is to just multiply it out, like I said to do. So this is 9x hat cross x hat, so forth. Oops, cross here. Okay, 2 of these terms vanish because, again, unit vector cross of itself gives 0. These are both 0. X hat cross y hat is what? Z hat. And what is y hat cross z hat? Y hat cross x hat is negative. And so we have 9 minus 9 in the z direction, which is 0. Right? Good. Okay. Now, how many of you know how to do the determinant? The determinant, yeah. Okay, so at least one of you doesn't, and I suspect a few more. So I won't spend a lot of time today. We'll do this on Wednesday. It's a quicker way of doing cross product using the determinant. And so this would be a quicker way of calculating it. And that's what I did. I worked this out at the bottom of page 2 on the homework solution. You can see I did the determinant. Shows that this is 0 also. If this is not familiar to you, don't panic yet. We'll go over this in class on Wednesday, the determinant. It's just a quicker way of doing the same thing. Okay. And in fact, I use the determinant throughout the rest of the homework. But you don't have to do that. You can just expand it out like we did here. You can do it, expand it out, collect all the terms. And remember, x hat cross y hat is z hat. Y hat cross x hat is negative z hat. You just remember those. And make sure you don't get any signs wrong. It'll come out right. Okay. So I'm not going to do any more of these through 10. These are more cross products. Okay, just exercises with Cartesian components doing cross products. Really good thing to do with grad students in the Physics Learning Center if you're still rough with this, but you got to get it down. It's got to be like this. right? This is basic stuff for physics majors, and it's got to be something that you don't have to think twice about doing. It's, oh yeah, I know how to do that. Okay, so number 11, find the magnitude and direction of A. So we found, remember, A is 3x plus 3y, and we found the length of A is 3 root 2. So how do we find the unit vector in the A direction? We know the vector and we know its length. How do we find the unit vector? The vector divided by its length. That's always true as long as we're dealing with a vector that doesn't have 0 length. Right? So this is 3x hat plus 3y hat over 3 square root of 2. So this is equal to x hat plus y hat over square root of 2. Let's prove that that has unit length. God bless. So this is a check. This should have unit length, right? So I have the 1 over root 2 times 1 over root 2 is a half. And then I have the dot product of x hat plus y hat with itself. Expanded out, I get 2 terms, x hat plus y hat. I get a factor of 2, right? So that indeed has length 1. Everybody okay with that? Another way of saying it is that it's 1 over root 2 squared plus 1 over root 2 squared, right? It's the square of each component added to itself. So that's 1/2 plus 1/2. It is indeed 1. Okay. Similar for number 12. Find the magnitude and direction of another vector C. And also R. R is kind of the generic name for the position vector. So R hat is going to be R, the vector R, over its length. And the vector is x hat plus y hat plus z hat. This is a general position vector. And this length is going to be the square root of x squared plus y squared plus z squared. That's the direction, the unit vector in the direction of some general position. You have the location of some particle, and I want to know what's the direction. Just give me the unit vector along that direction. That's what R hat is. Everybody okay on that? Okay. So let's go on to the homework problems from the book. So 17 and 18, what I wanted from the book was to write out these vectors. This is in 2 dimensions. And so I wanted you to do what I just did for dot product and cross product before. So A is just some general vector. Just using lowercase now instead of uppercase, that's fine. So this, the use of this symbol here, let me point this out. The use of this symbol, A here, comes from the fact that this is, we're using the letter A here. So we're just borrowing the letter for it in the symbol and writing the subscript to indicate the direction. And the same thing for B. Okay, you expand it out, you get 4 terms. Most of the terms, in this case half of the terms, vanish. And you get A dot B. Ooh, let me do it in black. A dot B is easily calculated if I know already the Cartesian components of the vectors A and B. I just multiply corresponding components, add them together. Okay? And then also the cross product I just worked out for you. Okay, how about, let's see, number 18 has to do with the relationship of the cross product to the area of the parallelogram. Is everybody clear on that? Why A dot B gives you the parallel part and A cross B gives you the perpendicular part? of the two vectors in relation to each other. Do you want me to draw that again?
Could you go over that again, please?
Yes, ma'am. Okay, so let's take A and B, and let's look at A dot. No, this is about cross product. So let's take A cross B. Okay. Now I can choose to draw this. I'm going to tilt my head so that A is along the horizontal direction. So here is A. I'm going to tilt my head so that A is horizontal. And here is B. Okay. Now, I want to understand the meaning of the cross product from this figure. And so what I'm going to draw here a line. It's called the perpendicular. What I want to form a right angle there. And that's important to get that step right. I take the end of B and I draw a perpendicular straight down so that it's perpendicular to the direction of A. And there's a right angle there. Okay. So, and here's the angle between the two. So let's draw this triangle over to the side here. This is what I have here now. So, what is the length of that vector? It's called B with an arrow over it, so we give it a general name, which is just the letter B. Right? B is the length of the vector B. And that's the hypotenuse of this right triangle. That angle is given, this is a right triangle here. Okay. So, given it's a right triangle, now tell me how long is that horizontal piece right here? This side and that side. I want to know both sides in terms of the hypotenuse and the trig functions. Sorry, say again? This is going to be B parallel. This horizontal part will be called B parallel, but in terms of the theta and the length of B, what is it? Cosine. Yes, sir. The B times the cosine of theta. And how about the vertical piece?
B sine theta.
Thank you. B sine theta. We also call these two B parallel and B perpendicular, meaning the part of B that's parallel to A and the part of B that's perpendicular to A. So you see the height of this thing that we drew over here, this piece, the height of that, the length of that is B perpendicular. It's B sine theta. Okay, so given that, then I can see the trick now is to see that this forms a rectangle here. And the trick is to see that, and of course, the length of A is the width of the rectangle. This is A. The length of the rectangle, the width is A. The height is B perpendicular, which is B sine theta. So the area of the rectangle is A times B perpendicular, which is also A times B sine theta. And the trick is to see that that's the same, the area of that rectangle is the same as the area of the parallelogram. And that's in question number 22. I've drawn a figure there to show you how to do that. If you extend this out here to make a parallelogram, this area is the same thing as this area. So you're just shifting it over to make a rectangle instead of a parallelogram.